This is HLAA day number 8 for vectors. We talk about lines, planes, and angles. And one additional topic that we're going to toss in there is shortest distance. Okay, the shortest distance from a plane to a point. Now this can be applied to multiple situations, whether it's plane to a point, line to a line, all that sort of stuff. So let's go ahead and take a look. Okay, so I want to revisit what was mentioned before about a line and a plane and the relationship that they can have. So 3 different scenarios. The first scenario is non-intersecting parallel lines. Okay, so let's take a look at that. Let's take, non-intersecting parallel plane and line. So here's pi 1. All right, and here's a line, L1. Let's say that there's separation there. Those two would be parallel if they never intersect. So we can look at that from the profile view on the side. Here's pi 1. And of course, here's L1. So you can kind of see it from the side there. Those would be parallel, non-intersecting. Okay, the second option would be intersecting, whether that's at a right angle or not. Let's take a look at a line and a plane in this scenario. So here is a plane, let's call it pi 2, and a line that intersects the plane at some point P. Let's call this point right here P. Okay, here is your line L2. Okay, there would be an example of a line intersecting a plane. Now the angle, right here, that could be a right angle, could be acute, could be obtuse, depending on what we're looking for. So clearly, if I were to look at this from the profile view, here's pi 2, and of course, L2. We're going to look at how to find this angle, right? This acute angle between a line and a plane in a few slides here. Third scenario, a line is contained in the plane. All right, pretty easy to see that if I had a plane, let's call it pi 3. People are laughing. Really think this is fun? This isn't fun. And a line L3, that all the points on L3 also satisfy pi 3. So therefore, I could sketch from the side and I'd see, here's pi 3 heading off in that direction, and of course here's L3, right, as a subset of that plane and contained in it, right? I wouldn't necessarily be able to see that from the side, seeing that like this is contained entirely inside that plane, but it's just a nice profile visual. Okay, let's get into a few examples here. Okay, let's talk about this example here where we take a plane, which is given. Right? We've got this plane 2x plus y minus z is equal to 3, and 3 lines given below. Okay, so I got line 1, line 2, and line 3. So let's classify the relationship between the plane and each of these individual lines. Okay, so what we need to do is we need to start with the normal to the plane. Okay, so I'm going to write out the normal to the plane, which is 2, 1, negative 1. I can see that clearly here. Okay, now as we consider, one of 3 scenarios will occur. All right. The first scenario is that our line, let's call it L of t, will be perpendicular to pi. Okay, so what would have to be true for our line to be perpendicular to our plane? Okay, what would need to be true is that the normal of pi is parallel to our line. Right? So if the normal of pi is parallel to our line L1, L2, or L3, then the plane and the line are perpendicular to each other. Okay, the second option is that our line is parallel to pi. Okay, so that that kind of opens up two options within just that scenario. So I'll get to that in a second here. Okay, so how do we know that that's true? Well, if that's parallel, then what's true is the normal is perpendicular to the line. Okay, which also means that the normal dotted with the direction vector of the line is equal to 0. Okay, now that opens up one of two options, right? If the line is parallel to pi, then option A is that they are, well, they're non-intersecting and parallel. Okay, option B is that the line L sub t is contained, right, or is well, fully contained in the plane. In that plane pi. So we have to do a little extra work if we get a parallel situation. And the third option, if neither one or two are satisfied, is that we just have intersecting, I'm gonna run out of room, intersecting line and plane, but it's non-orthogonal. Okay, so it just wouldn't be a right angle. Okay, so let's see which scenario we get for each one. Okay, so how do we go about this? Let's take L1, L2, and L3, put them in parametric form to start. So L1 will be -1 plus 2 lambda. Its y component will be 3 minus lambda. Its z component will be -2 plus 3 lambda. Okay, its direction vector, let's talk about that because that's going to be important as well. The direction vector of L1 is going to be 2, -1, 3. Now I can see those values directly from coefficients of lambda, 2, -1, and 3. Okay, let's do the same thing for L2. Okay, L2, x, y, and z components in parametric form. We'll have 2 plus mu. I have to use a different parameter here. I'll have 0 plus 2 mu, and I'll have -1 plus 5 mu. Direction vector for L2, of course, will be 1, 2, 5. Okay, same thing for L3, x, y, and z. Okay, x looks to be 0 minus gamma. We'll go with gamma for our parameter. -5 plus 4 gamma for our y component. And z will be -3 plus 2 gamma. And the direction vector for L3 is going to be -1, 4, 2. Okay, now as I look at each of these and my normal above, I can see, right, that none of these, right, 2, -1, 3, 1, 2, 5, -1, 4, 2, none of them will be a scalar multiple of the normal of pi. So what do I mean by that? I mean that the normal of pi is not equal to some constant times L sub t, where k is in R. That just means I can't multiply any one of those direction vectors by a constant and have an equivalent vector to the normal. Okay, that means that for none of these will the normal be parallel to the line. Okay, so none of our lines will be perpendicular to pi. Okay, so we got to do a little bit of work here. That was nice because that eliminated one of the options for each one of the three. Okay, so now we have to check option 2, right? In question, is the line parallel to the plane? And then we'd have to check the two conditions A and B under that. All right, so let's take and look at this condition right here. The normal line dotted with the direction vector of each line and see if it equals 0. Okay, so I'm going to take the normal in each scenario. I'm going to take the normal for pi and dot it with each of the individual direction vectors. Okay, so for the first one, I would have 2, 1, -1. I'm going to dot that with positive 2, -1, and 3. All right, what does that come out to be? Well, that's 4 minus 1 minus 3, that equals 0. Okay, so L1 is going to be parallel to pi. We don't know if it'll be non-intersecting or contained in the plane quite yet. So we still have some work to do here. So we got work. Okay, let's look at L2. So if I take n, which is still 2, 1, -1, and I dot it with 1, 2, 5. Let's see what we get there. I get 2, I get 2, I get -5. That's equal to -1. Since that's not equal to 0, since the normal dotted with the direction vector of line 2 is not equal to 0, then we know that L2 is intersecting non-orthogonal. Okay. L2 and pi intersect at a non-orthogonal angle. At an angle not equal to 90. Okay, easy enough. Okay, let's look at L3. We'll take n, yet again, 2, 1, -1, dot it with L3, direction vector of L3, -1, 4, 2. Okay, and we're going to find out what that equals. That's -2 plus 4 minus 2. That's equal to 0. We got more work to do on that. So when I say more work, what that means is that we've satisfied that the normal dotted with the direction vector is 0. Now we need to determine, is it non-intersecting parallel, or is the line contained in the plane? So what I'm going to do is for each of these lines, and I'm going to utilize some of my space below. For each of these lines, I'm just going to take something simple, okay, and I'm going to plug lambda equals 0 into my line for L1. So if lambda equals 0, then L1 is the following. Okay, I know that the initial point for L1 is -1, 3, -2. So if I plug a 0 in for lambda, it doesn't matter what my direction vector is. This is going to be the point at which that line will occur, will be, right, at lambda equals 0. Okay, so what I want to do is I want to see if this line, or this point, is contained in the plane. Because if that point's contained in the plane, and the line is parallel to the plane, all other points have to be in the plane. So I'm going to take pi 3, okay, which is 2 times x plus 3 times y minus z, excuse me, not 3 times y, 2 times x plus y minus z is equal to, what we want it to be equal to up here is 3. So we're going to see what this comes out to be. So I'm going to plug the values for x, y, and z when lambda equals 0 and see what that comes out to equal. Well, that'd be -2 plus 3 plus 2. Well, that comes out to be 3. Therefore, the point -1, 3, -2 is contained in pi, and since L1 is parallel to pi, then L1 is contained in pi as well. Okay, let's do the same thing for the third line. Let's set gamma equal to 0. Okay, so if gamma is equal to 0, you can do the same thing. You can pretty much drop off your direction vector because that'll take care of that. And what we're looking to do is to see if 0, -5, -3, right, is a point that satisfies the plane. Okay, so I'm going to do the same thing that I did before. I'm going to take 2 times x plus y minus z and find out what that equals. So I plug in a 0, a -5, and a -3. What that comes out to be is 2. Now 2 is not equal to 3. Why is 3 important? Because that is the constant that satisfies this plane's equation. Since 2 is not equal to 3, then that means that the point 0, -5, -3 is not contained in pi. And if it's not contained in pi, since L3 is parallel to pi, then L3 is also not contained in pi. And this is kind of redundant, but now you can say that L3 is non-intersecting and parallel to pi. Okay, that's it for that question. Let's continue on to the next. All right, let's take a look at this example to find angles between planes. So let me just make a quick sketch of pi 1, pi 2. So pi 1, what does it look like? Well, maybe like that, I don't know. Pi 2, what does it look like? Well, maybe like that. Well, how do I know that they're not the same plane? Well, their normals are different, right? So the normal for pi 1 is going to be 1, 2, and negative 2. Okay, because if their normals are parallel, the planes will either be parallel, non-intersecting, or concurrent. Okay, and 2, or a normal for pi 2 is going to be 2, negative 3, negative 6. Okay, so clearly these are going to be intersecting planes. They'll intersect at a line. You can't really see the line, but it would occur right here. It'd be coming at us. All right, what we want to do is we want to find this angle. I'm going to call it phi. Okay, so what we do is we project the normal, right? So here's normal 2. Why did I call that a 3? That should be a 2. Here's normal 2. Okay, it's perpendicular to pi 2, right? Comes right out of pi 2. And here's normal 1. Comes right out of pi 1. What's cool is that this is now a kite, right? Where this angle here is theta. Now, how are theta and phi related? Well, theta plus phi, if you look at properties of a quadrilateral, these are two 90-degree angles. That means these angles have to be supplementary, so they're going to add up to pi units. Okay, so essentially what I'm going to do is I'm going to find that angle theta, take it away from pi, and that'll give me phi. So phi will equal pi minus theta. So how do I find theta? Well, that's the same as finding an angle between two vectors. Right, I'm going to find the angle between normal 1 and normal 2. Okay, so how do we do that? We take the cosine of theta, which is equal to normal 1 dotted with normal 2 over the magnitude of their products. All right, this is going back a couple of lessons, but it's attainable and feasible. So N1, normal 1 dotted with normal 2. That's my red vector times my blue vector. If I do the work on that, normal 1 dotted with normal 2, I get 2 minus 6, which is negative 4, plus 12, that's going to be 8. Okay, now let's look at the magnitude of each of the normals individually. The magnitude of normal 1 will be 1 plus 4 plus 4, which is 9. Square root of that will be 3. The magnitude of normal 2 will be 4 plus 9 plus 36, which is 49. Square root of that is 7. Therefore, the cosine of the angle between the normals is going to be 8 over 21. Thus, the angle between the normals, theta, we're calling it, will be inverse cosine of 8 over 21. Okay, so theta comes out to be a certain number, right? And I don't really even care what it is. What I'm worried about is finding phi. Phi is going to be pi minus this value. Okay, so don't do any intermediate rounding. We want phi, the angle between the planes. Okay, so the angle between the planes to three significant figures here comes out to be 1.96 radians. All right, we use the normal to find the angle between the planes. Let's continue with the next example. Okay, we looked at angles between planes. Let's look at angle between a line and a plane. So find an acute angle in radians to 3 sig figs between the line and the plane. So let's look at what this might potentially look like. So I'm going to do my plane here. I'll just call it pi. I'm going to sketch this in blue. Okay, so here comes our plane pi. All right, and then let's take this line and we'll just call it L. Keep it simple. And let's say L intersects and kind of comes up this direction. Here's L. Okay, so let's put some perspective on this graph, right? Okay, so the angle that I'm seeking is this angle here. I'll call it phi again. Well, what I'm going to do is I'm going to sketch a nice little right triangle here. And what I'm going to do is I'm going to find the angle right here. I'll call it theta. And that's the angle between this blue dotted line, which is the normal of pi, and the direction vector of L. So essentially what I'm doing is I'm going to find theta, which is the angle between the normal and the direction vector of L. Okay, so I'm using the same formula I just did on the last page. Okay, so the cosine of theta is going to be equal to the direction vector of L dotted with the normal of pi over the magnitude of the direction vector of L times the magnitude of the normal of pi. Okay, so I got to do a little work to kind of dig out what is what here. Okay, so I'm going to put L in parametric form. So I'll do x, y, and z. That'll expose the coefficients of lambda, which are the values of the direction vector for L. Okay, so in parametric form, we would get -3 plus 2 lambda. We would get 5 plus 4 lambda. And we would get -1 plus 2/3 lambda. Okay, so you can work your way through that and find, make sure that you can come up with that parametric form. That's important that you can do that. All right, so the normal vector to pi is pretty simple. It's going to be a 1, a 2, and a -2. Okay, so let's find the direction vector of L. The direction vector of L will be 2, 4, and 2/3. Okay, so now what we need to do is we need to find the direction vector of L dotted with the normal of pi. Okay, so that's going to be, let's look at the numbers. 1 times 2 plus 2 times 4 plus -2 times 2/3. Okay, that's interesting. That actually comes out to be, you can check the math on this, 26/3. Okay, check me on that, make sure I'm right. All right, we need the magnitude of the normal vector. Magnitude of the normal vector, well, that's going to be 1 squared plus 2 squared plus 2 squared, which is 9. Square root of that will be 3. Okay, the magnitude of the direction vector, L1. Okay, so I'm going to square each of the components. So 2 squared is 4, 4 squared is 16, and 2/3 squared is 4/9. Okay, so I got to do a little work to clean this up, because that'll be helpful if I do. Okay, so that'd be 36/9 plus 144/9 plus 4/9. And I'm going to take the square root of that. Okay, so the magnitude of the direction vector of L is going to end up being the square root of 184 over the square root of 9, which will be 3. Okay, we got our direction vector, or our dot product, which we call the scalar product. We got the magnitudes of each of the vectors. Let's set this thing up. Okay, so the scalar product, 26/3. The magnitudes, I had a 3, and I had a square root of 184 over 3. Okay, so I can clearly see that these 3's will reduce. I'm going to bring this 3 right here down into the denominator, so the cosine of theta will be 26 over 3 root 184. I'm going to do a quick calculation using inverse trig. So theta will be equal to the inverse cosine of 26 over 3 times the square root of 184. Now, before we go any further, let's talk about this. This is no longer a kite that we're looking at. This is a triangle. So in a right triangle, theta and phi, which are the acute angles, those angles should add up to pi over 2. So theta plus phi is pi over 2. Therefore, phi is pi over 2 minus theta. So I'm going to find phi by taking pi over 2 minus this thing, inverse cosine 26 over 3 times the square root of 184. Okay, what that comes out to be when I use my calculator is 0.693 radians. All right, there you have it. That's how you find an angle between a line and a plane. Let's continue to our last example. Okay, a couple interesting things here. Part B is interesting, and it's something that I'm actually going to cover in a separate video. But it asks for the shortest distance from the origin to the plane pi. Okay, so anytime you have a situation like this, right, and you have a point, in this case the origin 0, 0, 0. Okay, to find the shortest distance, right, which would be a distance clearly that would have to be perpendicular to the plane. What you're actually going to do to find that distance is take the absolute value of d over the magnitude of the normal, and I'll explain why in a different at a different time. So in this case, d is equal to 14, and magnitude of the normal we'll find out in just a minute. Okay, so part A, let's get into that first. Part A says, given that L meets pi at a point P, find the coordinates of P. If you can't tell by now, the parametric form of any line is very, very useful, so get used to kind of going there. There are other methods, but that's where I would always go first. It's very helpful, especially when dealing with lines and planes in the same problem. Okay, so there's a parametric form there for L. Okay, what I want to do is I want to find the parameter lambda such that L meets pi. So what I'm going to do is in pi, which is 4 times x plus 3 times y minus z is equal to 14, I'm going to plug in x, y, and z in terms of lambda. Okay, so I'll have the following expression. What that's going to allow me is the lambda value such that the line intersects the plane, which is exactly what I want. I'm looking for P, right? So this will be the lambda that coordinates or times up or aligns with P. All right, so let's find what lambda would be. This will be 4 plus 24 lambda plus 15 minus 6 lambda plus 3 minus 2 lambda is equal to 14. Okay, combining like terms, it looks like I get 16 lambda, and what is that, 1922 plus 22 lambda, oops, not lambda, just 22 is equal to 14. Therefore, 16 lambda is equal to negative 8, which means lambda is equal to negative a half. So when lambda equals negative 1/2, the line intersects the plane. That's obviously very helpful. So our point, this will be point P, will be equal to 1, 5, negative 3 plus negative a half in for lambda times the direction vector 6, negative 2, 2. Okay, it's just a linear equation, that's all it is. Thus P, which equals this point of intersection x, y, z, will equal 1 minus 3, which is a negative 2, okay, 5 plus 1, which is equal to 6, and negative 3 minus 1, which is a negative 4. So whatever this plane and line look like, right, I don't know what they look like, but I can tell you that this point right here is point P. Right, that's the point of intersection, and that occurs, right, when lambda equals negative half. Okay, now let's look at part B. We'll just do the mechanics of this. But like I mentioned earlier, I'm going to take the absolute value of d, and that's a good reason right there why I always just make d greater than 0, right? Which changes the direction of the normal, right? Because it changes all the values, coefficients for x, y, and z. But when it comes to this equation, you don't run into issues if you forget to take the absolute value over the magnitude of the normal. All right, and this will equal capital D, which is our distance. So the magnitude of the normal, we just got to do a little algebra on that. Magnitude of the normal will be the square root of 4 squared plus 3 squared plus negative 1 squared. Where did I get those coefficients of each of those components? So that's 16 and 9 and 1, that's 26. So this would be the square root of 26. Okay, that's the magnitude of the normal. I know the absolute value of that constant d is 14. That'll equal our distance, which, depending on what form they ask you to put it in, I'm going to put it in the form 7 root 26 over, oh gosh, did I really just write a 16 there? Okay, over 13. So either of those two would be acceptable answers. That would be the shortest distance, right? The shortest distance from the origin to the plane. All right, guys, that's it for day number 8. We'll see you guys in the next video.